Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, good afternoon, everyone. So we're especially delighted to welcome this year's Birnbaum speaker. Professor Varadhan has transformed quite a number of areas in probability, and just to give a small sample, the Donskar-Varadhan theory of local times, in general, his work on large deviations that we'll hear something about today, hydrodynamic limits. One of my favorites is his introduction of the self-intersection local time, and I could go on, but instead let's have the speaker tell us about the role of compactness in large deviations. Professor Varadhan.
Thank you very much, Yuval. It's a pleasure to be here. So there are many problems in analysis where we use compactness of space in some routine manner, and sometimes it's not there. And when it's not there, you have to work harder. And the hard work takes different forms. So I will look at a couple of examples of various types, things that we do to avoid the issue. And then I'll give one example that leads to some interesting calculation. So what is in large deviation theory? One of the things we want to do is to analyze asymptotic behavior at certain integrals. These are integrals of the form exponential of a function with a large parameter multiplying it times certain family of probability measures Pn. And then we want to look at the tilted measure, which you throw in the density e to the nfx as the Radon derivative of Pn, and then normalize it by the expectation so that Qn is a probability distribution now, which somehow tries to maximize f, Now, the Pn itself has its own behavior. It's not uniform, and it decays locally, exponentially at different rate at different points. So actually, there is a fight going on between the function f, which wants to be large, but the cost it has to pay for picking a point x is I of x. So this fight has to be resolved, and one can conclude that Zn is asymptotically like n times exponential of n times the supremum ff minus I. That's one of the results in large deviation theory, which is not an easy result to prove, so long as you can interpret what dPn decays like exponential minus I of x, you have to give a meaning to it, because the left-hand side is a measure defined for sets, and right-hand side is a function defined on points. So that has to have an interpretation. And one of the things we want to prove with the interpretation is we want to show that the measure Qn concentrates at a single point A, provided the variational problem has a unique solution. If at some point A, f minus A as a maximum, strictly larger than all the other values, then we want to show that the Qn measure concentrates at the point A. So now what do we mean by this expression that dPn behaves like exponential minus Ix? Well, we are interested in log of Pn, and we want log of Pn of A normalized by 1 over n to behave like infimum of I of x over the set A. Even this cannot be true for all sets, because if you look at a single point set, I could be finite at that point, and Pn of A usually is 0 for single point sets. So this again has to be interpreted carefully, and the interpretation is you get a lower bound for open sets, and an upper bound for closed sets, just like as in limit theorems in probability. Now, for open sets, it's easy because usually these results are obtained for small balls by some tilting argument. You make law of large numbers for the tilted measure to localize at that point x, and you figure out the cost of tilting, and that gives you the exponential lower bound. So the lower bound, if you get for a small ball, that's enough for any open set. You can just optimize the location of the small ball, and then you get the inequality for open sets. The upper bound is for closed sets. And how do you obtain the lower bound? How do you obtain the upper bound? Usually, in probability, what you do is you use Chebyshev's inequality to get the upper bound, right? So you use the inequality, the probability that some f is bigger than L is bounded by e to the minus n L times the exponential of n times f. It's like a Chernoff bound type of thing. And then if f is a nice function, you can find a ball around some x of radius epsilon contained in this half space, f less than or equal to L. So that gives you an upper bound for a small ball. And the upper bound for a small ball is basically e to the minus n times f of x times the exponential, the expected value of the exponential. And the expected value of the exponential perhaps grows like exponential of some constant, which depends on f. So in the end, the best possible upper bound you can get is a decay rate, which is the best possible Chebyshev's inequality you can dream of. Okay. But this is only a local bound for a very tiny ball, and you cannot control the size of the ball because it's a soft argument in some sense. Okay. It depends on where the soup is attained, what kind of a bad f you have. And what do? You use the inequality, which is simple inequality, the probability of the union of two sets. You can bound it by the sum, and you can write it by the twice the maximum. The beauty in large deviations is by the time you take the log and divide by n, the 2 goes away. Once the 2 goes away, then you can cover a compact with a finite number of these things. So immediately you get an upper bound for compact sets. So you need finite covering. So you can estimate the probabilities in question for compact sets. The rate of convergence would be okay. If the space is compact, we're done. This problem is solved. Often these spaces are not compact. Then you have to do something else. What are the things you could do? Well, you can find a big compact set and show that what happens outside is not relevant. Now, in Prohorov theory, in order to show that something is not relevant, you have tightness estimates. You show that the probability of a complement can be made arbitrarily small. Here, we are interested in large deviations of rate n. So we have to show that outside the compact set, the probability decays faster than any exponential you can think of. So basically, the constant of decay has to be very large outside a compact set. So you can sometimes do that, and that's called exponential tightness estimates that you derive. Or you can compactify the space. Okay, any space can be compactified, according to a theorem in points and topology. But then that has its own problems, because now once you compactify the space, it's not clear whether your function extends to the compactification or not. And then you have to get your local upper bound for all the points you have added in the compactification. So you have to have more or less a concrete compactification, not an abstract compactification, in order to do it. Or you can modify the problem. You can just, if you're interested in just estimating it, you can simply say, well, this integral is less than or equal to some other integral somewhere else, which happens to be a compact space. Then you can do that. And all of this have been tried, all just for Brownian motion and just for the local time. In different contexts, you can do different things. The Brownian motion local time is just a random measure, which is the amount of time that the Brownian path spends in a various sets A. And the space of measures is now the ambient space, because you think of LTA as a random probability measure. So you have a family of probability distributions in the space of measures in RD, and this is where you want to do your large deviations. And one knows what the rate function is locally. There's no mystery, because it's just it's a reversible process, a standard computation, that the local rate function is just the Dirichlet form of the square root of f. So the question really is, how do you handle the non-compactness here? The first attempt is to estimate, for example, the Feynman-Kautz formula for integrals like this for potentials v that go to infinity as x goes to infinity. Now, if the Brownian path wants to go too far, v kills it. So it's clear in this problem you can handle the non-compactness, because the non-compact part just doesn't count. And the asymptotic rate is just the infimum of the integral. We had the supremum because of the minus sign and so on. You write it as the infimum. One can also technically compactify the space. Well, the easiest compactification one can think of is the one-point compactification. So just add a point at infinity and say my space now is compact. And the rate function for the delta measure at infinity is 0, because the Brownian local time eventually wants to get away to infinity. So the neighborhood of infinity really means most of the mass is very far away. And so it's clear that the rate function at that point is 0. Now everything is compactified. But then the price you pay is you have to assume that the potential v goes to 0 or has a limit as x goes to infinity. Then you can subtract the limit, and it's just basically going to 0. So the class of functions that you can handle gets reduced considerably because of the compactification you used. So another thing you could do is you can replace RD by the torus. You can project the Brownian path that's wandering in RD to a Brownian path on the torus. And when the function you're trying to estimate is larger on the torus for the projected path than for the original path, then if you try to estimate it on the torus, it's good estimate on the whole space. And the torus is compact, so your estimates work for the torus. So you can sort of do the problem for a large torus maybe, and in the end let the radius of the torus go to infinity. There is no trouble interchanging the two limits, because you have actually domination in one case. And that has been tried too, and that works for the problem of Wiener sausage, because if you project the sausage in the torus has smaller volume than sausage on RD. Okay, so problems like determining the range of a random walk and things like that, projecting on the torus is a good method of compactification, because the projection overestimates. So now the problem I want to look at is the following thing on the local time. In d dimension, you look at this double integral of the potential 1 over mod x, and you want to analyze this. Well, here what works is replacing Brownian motion by Ornstein-Uhlenbeck process, because Ornstein-Uhlenbeck process is strongly recurrent, And you can get super exponential estimate for what happens outside a compact set. So you can do that, and you can show by, because the function 1 over mod x is positive definite, the integral is more for Ornstein-Uhlenbeck process than it is for Brownian motion. So comparison works here. It's not quite satisfactory for the following reason. When you modify these problems like this, use methods, comparison, and so on, it is enough to estimate the partition function z, t, and how it grows, and so on. But if you really want to prove that the measure qt defined by this tilting, the new measure, if you want to prove that it is, I think I made a mistake here. There is no 1 over t because I have used the local time already. Okay, it should be t in the scaling. So you cannot analyze this by modification because then a double limit is involved, and it's hard to control things. So what I'm going to describe now is some joint work with Chiranjeev Mukherjee, who is a postdoc at Munich. So let's look at this local time. And you have a function of the local time that we want to analyze. But this function is translation invariant, because if you translate the measure mu, it doesn't change. There are examples of this. The examples of such functions are our function, which is a function of 2 variables, or you can take functions of k variables, which are invariant under rigid translations. And then you integrate with respect to the product measure of the mu's. And these are functions that are invariant with respect to translations. So they have this property. And let's suppose these functions are tame, that whenever the separation distance between a pair of points goes to infinity, these functions vanish. So they're basically supported on points x1 through xk, which are tightly bound together. If they sort of drift apart, then the function vanishes. Our function 1 over mod x1 minus x2 has that property. And then we want to analyze the expectation of something like this. So now we have to go to the quotient space, because it's a problem on, if you want to, the problem has the translation invariance. So the natural space on which to do the large deviation is the quotient space of orbits of measures. Translation of it. This space is still not compact. Okay? So the question is, what is the compactification of the space? You can't get away with 1-point compactification here because the orbits, then all the orbits collapse, because at infinity everything meets in 1-point compactification. So you can't use that. So you need some other compactification. So the question is how to compactify. 1-point compactification is not suitable. It's not translation invariant. So let's take a function f which is translation invariant, continuous, and has this property of decaying when the distances go to infinity. And look at all such functions, not only for 1k, but all the various values of k, functions of several variables for all values of k. And then I look at these linear functionals, lambda f mu, which is the integral of this function against the mu. It's just some elementary points in topology here. These objects for each f are bounded, and the space fk are all nice separable spaces, because the space of functions of this type is really a function of k minus 1 variables that vanishes at infinity. So it's a nice separable Banach space. So a countable number of separable Banach space. So it's enough to choose a countable dense subset that works for everything. And then by diagonalization procedure, I can choose a subsequence that all these things converge. Okay. So a countable set is enough. And also one thing interesting that's to be noted is fk minus 1 in some sense a limit of fk. Because if I take a function of k variables, define it as a function of k minus 1 variables, multiply by a function phi of x1 minus xk, although this function phi has to vanish at infinity for this to be well defined in our class, but I can take the limit as phi goes to 1. If you take the limit as phi goes to 1, it's not a uniform limit, but it's a pointwise bounded limit. It's okay for integrals, because I can use the bounded convergence theorem. So then the integral fk with respect to the product measure will converge to measure the whole space times the k minus 1 dimension. So the k minus 1 dimensional integrals are recoverable from the k dimensional integral by a limiting procedure. So now what I want to do is choose a subsequence that all these limits exist. I can always do that. So now I have compactified the space in principle. But I have to know what is this linear function lambda f. Okay. Now the answer is very simple. Or there is another way of thinking about it, which is you define a metric between two measures, probability distributions mu1 and mu2. You look at this lambda fj mu1, which is a k-dimensional integral of fj. K depends on j because different functions, this countable sequence will be in different dimensions. And you compute the integral, take the difference, and it's the usual trick you do for a countable product of metric spaces. You put some weights in front so that the series converges. It's nothing special about it. And you try to complete in this metric, which is really saying that anything that converges for each function should be some limiting object. And then one way of choosing the weights is just usual choice. So here's the answer. The answer is the limit consists of collections of orbits, mu j, mu tilde, and their total masses of all the orbits. See, the total mass doesn't depend upon which measure you choose in the orbit. So these are sub-probability measures. Each orbit will have some probability, and you add them all up, you get something that's less than or equal to 1. That's the limit. And then the representation in terms of the limit, you compute the same integral as you did before for each member of the orbit and add them all up for the different orbits. The intuition behind this is very simple. How can a sequence mu(n) fail to be compact? The whole mass can run away to infinity. And then the mass can split into two pieces. They're running into infinity in different directions. That can happen. Or you can have a Gaussian distribution with a very high variance, so the mass just goes away. So in the first case, the orbit actually converges to a different orbit. The orbit corresponds. In fact, the orbit doesn't change at all because I have the same mu. Here in the limit, I get two pieces, mu1 and mu2, of mass 1/2 each, but the two pieces are identical. The same 1/2 mu appears twice. In the third case, it just becomes dust. So the compactification consists of various pieces that you can pull together, which are these sets of orbits, and then something that's disappeared. into dust. That's why the total masses, when you add up, you get something that adds up to p, which is less than or equal to 1. Okay. And the same orbit can occur twice, so you have to count, you have to list the orbits with the understanding that you can list the same thing twice. Of course, it's possible that your collection is empty, which means everything went to dust. So for every function f, your linear function goes to 0. Or you can just have a finite number of orbits, or you can have a countable number of orbits with masses getting smaller and smaller and adding up to something less than or equal to 1. So that's intuitively the compactification. And you have a metric there, which is you look at lambda f psi, which is this integral summed over all the orbits, and the metric is the same metric, except instead of a single measure mu, now you do it for each member of the orbit and add them up. It's clear D is a metric, but if you want to show it's really a metric, you have to show that the distance is 0 only if the two sets of orbits are identical. You have a problem here because you have one set of orbits here, another set of orbits there, and you have some objects which are equal. But the objects are collective objects, and now you have to match orbit with orbit if you want to show that the two sets of orbits are identical. So there's a matching problem to be done. So let's note that if you take a function of 2k variables, which consists of a function of k variable repeated in 2 blocks, but the blocks linked by something, and the linking object can tend to 1, and then by bounded convergence theorem, what you will converge to is sum of squares of these functions. So that means if you have integrals identical for 2 orbits, then their squares are also identical, and you can repeat it for any power, and so all the powers are the same. That means you can identify individual pieces. So you would think that now that you have identified individual pieces, then you're done, but not quite, because all I know is that any integral appears on this list. But for different functions, it may appear in different places. I had to locate them all in the same place. Okay? That requires an argument. So for each f, okay, I will come to that in a minute. But what happens if you know that even if you succeed in doing it, what you know is the multiple integral for each f is the same for 2 different orbits? Then you have to conclude that the 2 orbits are the same. The measure, what do you mean by that? So the real problem is to show that if you have 2 measures mu and nu, which satisfies this relation for every function f in fk, and for k bigger than or equal to 2, then mu is a shift of nu. That's what you have to prove. Okay, how do we do that? Well, let's take the characteristic functions. So the characteristic function is you can't use the characteristic function at all arguments, because you have to be shift invariant. That means you can look at the product provided the sum of the ti's are 0. That would be a bounded limit of functions that we admit. Okay. So you have two characteristic functions phi and psi with the property that their product are equal at all arguments when their sums are 0, then is one an imaginary exponential of the other. Well, first, the easiest choice to take two t's is to take t and minus t. Then it tells you phi t times phi minus t is ct times c minus t. We know that phi minus t is the conjugate of phi t, so it tells you that absolute values are equal. Then you write phi t as psi t times chi t. Then you would like to prove that chi t is an exponential. You take two of them. Instead, now take 3, and that tells you chi t1 plus t2 equals chi t1 chi t2. But then that's only for t's that are not 0. Phi t shouldn't be 0. If it's 0, then chi is not defined. But near the origin, they're not 0. Okay. So, and away from the origin, you can prove that chi n t is chi t to the nth power, because n positive t's and 1 minus n t work. And that concludes that one is a shift to the other. So now we are faced with the problem of matching individual ones. That is, for each f, this lambda f mu occurs somewhere on this list. So let's take one orbit, and I compute for that orbit the bunch of numbers lambda f mu. All these numbers are going to come on the other list, which is a collection of orbits somewhere. But I want to show that they all occur in one orbit. And then I'll match these two orbits, peel them away, and repeat it again. Then I'll be able to match the two orbits. So the question is, bare category theorem helps. Now, f, I can always let f tend to 1, because 1 is translation invariant and can be a limit of these things. So that means the collection of total masses are the same for the two sets of orbits. So it tells you that the size of the two orbits are the same, and the total masses are all the same. So in particular, if you give me the mass, there can only be a finite number with that mass. So if I know lambda f mu for all the f for 1 mu, I definitely know the total mass, and there are only a finite number of things at the other side with which I could possibly match. So I consider this set of all functions in some fk such that it coincides with that nu. So this is a set of functions in fk for which the integrals match those that I get for a nu on the other side. These are closed sets, and their union is all of fk. By bare category theorem, one of them has an interior. But once two linear functions agree in an open set, they are the same. So that's the end of that. Okay? And then you have to worry about what happens different k. But notice I said that fk minus 1 is a descendant of fk. So there are only a finite number there. I have a matching for every k. Eventually, somebody has to match infinitely many k's, and then I can come down and they will match all the k's. Okay? So that one of them has to have all kinds of very large values of k, and you can come down. Okay. Now, if you want to show that the object I have is really a compactification, then I had to show that the original set was dense. That's not very hard, because if I look at this, what I have in the completion, I have a bunch of measures with masses adding up to some number less than or equal to 1. So take these measures, put them in space, but take compact subset of these, with outside of which the mass is very small, you can always approximate, and then spread them out as far as you can. And it's clear that that's going to approximate this, because your visualization of an object that approximates this is just different pieces that are very far away from each other. So you can embed your mu1, mu2, mu_n into a single measure with pieces that are very far away. So it's clear that the original space is dense here. But then it's not we didn't really prove the representation theorem, if you remember correctly. I just mentioned it. I didn't prove it. I mentioned some consequences of the representation. I proved the uniqueness of the representation and so on. I never proved the existence of the representation. And that is the crux of the compactification. I need to show that if you give me any sequence of measures, I can somehow extract from them these pieces. Okay? And you use concentration functions to do that. So you define the concentration function of a measure to be the supremum. How much time do I have?
20 minutes.
Oh, plenty. I won't need that. So use concentration function to do this. You define this, you look at the ball of radius r, translate it around, take the maximum probability you can recover from it, and that's the concentration function of radius r. And any probability measure by just the tightness argument, if r goes to infinity, this goes to 1. Now if you give me a sequence, I can choose a subsequence that converges, and the limit qk, as k goes to infinity, its monotone has a limit. That limit need not be 1. It's something that's less than or equal to 1. In some sense, you should think of q as the biggest recoverable piece. And all these calculations depend only on the orbit, so it's done on the quotient space already. If q equals 1, that means after some translation, the measures that themselves are tight, so the sequence after translation converges, so the orbit converges to a single orbit. If q is 0, the probability for any ball goes to 0 no matter where the ball is. That means the measures converge to real dust. And in the limit, that corresponds to 0 orbits, and the total mass is 0 in that case. If q is in between, you can recover a big piece, because the concentration function gets values close to q, so you can pull it back and you'll have something which has mass almost q. Well, make it at least q by 2. You can almost get q, but it work a little harder. But you don't need to do that. You can at least mass q by 2, but then grow it as big as it can, that particular collection. You bring it in here, and then you see what the limit is as you increase the radius. Okay, you have collected this biggest piece. It's not 1, it's something less than 1. And then you look at the measure that's left over. That leftover measure can't be anywhere near the vicinity of this measure. Because if it were in the vicinity of this measure, your radius, by increasing more, you would have recovered more. The fact this is the maximal amount you could recover means the rest of the mass is very far away. And then you remove this piece and work with the rest of the mass, and you remove piece after piece after piece, and then you can show that that's a subsequence. You have to do diagonalization a million times. In the end, you get a subsequence that converges, and the convergence is in the metric that we have. So this is the compactification that you do. Repeat and exhaust. So now we have to worry about doing large deviations in this space. Okay. First, there is some, the orbit is not compact because it's orbit by all of RD. So a neighborhood of the orbit is a lot bigger than the neighborhood of the original measure, because you have to do all the translation. But what saves us is a Brownian path is not going to wander too far. You know, in time t, typically it wanders a distance root t. If I give it range t, then I am in the large deviation range. If I give it distance t square, then I am beyond large deviation. So I am willing to say my Brownian path is allowed to wander a distance t square. So the local time is essentially going to be limited to something of volume t square, which is polynomial in volume. That's going to affect the exponential rate by an extra polynomial factor, which I don't care about. So the fact that the orbit is big doesn't matter. So I can limit myself to a definite sized orbit. There is a way of doing it. You define a certain function. See, the way you compute the large deviation rate function is you need to have some integral which you can control. The integral you control here are Feynman-Kautz formula. Feynman-Kautz formula tells you how to control integrals of exponentials. In fact, if the exponential is of the form Laplacian, 1/2 Laplacian u over u with a minus sign, then by martingale property, you can, its integral exponential of its integral is bounded by 1, basically. So there are lots of integrals that you know of exponential Feynman-Kautz type whose expectations are bounded by a constant. So you use all of them and look at the best you can do, and that's the large deviation upper bound. That calculation gives you gradient f square over f 1/8, and it's a simple calculus of variation. So that's what we need to do, except we can't use one function. We have to use a function here, a function there, a function here to capture all the bits and pieces. So you have to take the supremum over all possible functions over all possible locations. But a little perturbation doesn't change much because these functions are all continuous, so there is no problem in having a little variation. But then your volume is only t square, so you can do it by a polynomial number of these things, and you know, it's a mess to write it down, but there are so many parameters, you know, and you look at this integral, the expectation of the exponential of this without the 1 over t is bounded by some number. And then you look at the supremum of these things, that's the lower bound you can get. That's the upper bound you can get. And these integrals are all bounded by Feynman-Kautz formula. Small variations change very little. And you don't have to shift by more than a distance t square. The sup is over polynomial many sets of AI. And if you do the infimum, you can separate out all the components, and then what you get for the rate function is the sum of the rate function. In the end, we haven't really discovered anything new. We have just justified the compactification and pretend that the space is compact. That's all. So now you go back to the problem in question. So I want to look at this function. This function has a singularity. That's an additional headache. But 1 over mod x is not a bad singularity in 3 dimensions. And usual estimation methods tell you that you don't have to worry about the singularity. For all practical purposes, you can pretend that's a bounded continuous function. Singularity is not. So if you do the variational problem now, you can do it in our space. And f is an L1 function. You can think of it as the square of an L2 function. And then 1 over 8 grad f square f becomes a Dirichlet form. And different components have different functions. And so the variational problem, so this is just what I get by doing the variational problem in the compactified space. And one can then prove that the variational problem is attained at a single phi of unit mass, which is unique up to translation. So there is a unique maximum for the variational problem on x tilde, and that tells you that the mass under Qt concentrates in the neighborhood of that orbit. The uniqueness of the variational problem was proved earlier by Elliott-Lieb in some other context, so that's definitely useful here. So the moral of the story is, in the end, you didn't need all this, right? But you needed it in order to be sure you didn't need it. Thank you.
Questions or comments? What you said reminds me, there's a, I think it's a British saying, would these precautions be so unnecessary had they not been taken? So, yes. So this variational problem that you zero, the large deviation for the specific potential, so it had some physical origin, motivation.
Yeah, it's
tell us a little about that.
I think Gordon knows more about it. Polar-round problem, which is a question of electrons sort of reacting with the field that they created themselves, some says in the past.
Because I know that, if you just fix one variable and just look at the potential as a function of the other variables, then the concentration of that along the random walk path has been extensively used by Lawler in studying intersection properties of random walks. So this seems to be tightly related to what you're doing here. It's worth looking at. Any other comments? Not let's thank Professor Vardan.